Well, welcome back everybody to Unit 2. We're going to start with Chapter 4, which is describing pulsed waves. And you're going to see in this chapter that we're going to hear a lot of the same concepts, a lot of the same ideas as we did in Chapter 3 when we were talking about those 7 parameters that go with sound. But now we're talking about parameters that go with pulsed waves. And you might be wondering to yourself, what do I care about pulsed waves? Well, let me tell you. Ultrasound, the way that we know it, the way that it creates images, has to do with a pulsed wave. So one of the biggest concepts that you're going to need to know, just kind of moving forward about ultrasound, is that it sends pulses out. And when the ultrasound machine sends a pulsed wave out, it has to wait for that pulse to return. It has to wait for the echoes from that pulse to return to create an image. So let me just diagram it for you really quick here. Again, we've got our transducer. Didn't really set this up before I got started. Let's try again here. Alright, so we have our transducer, and our transducer is going to send out this pulse. And that pulse then is going to travel into the body, hit what it needs to, and return back to the transducer. Now the transducer can't send another pulse until all of this information is received from the body. Now the other idea behind these pulsed waves is that we use one pulse to create one scan line. And so when you think about your picture, we get this sector view to our picture, and our picture is in there and it just shows up on the screen almost like magic, right? Not really. There's a lot of physics, there's a lot of things happening super quickly, like so quick our mind can't even keep track of it. What's happening is the one little pulse gets sent out, it travels down and back, and that's one scan line. Then another pulse is sent out, down and back, that's another scan line. Another pulse, down and back, another pulse, down and back. And these pulses, again, can't happen until all the echoes from this first pulse makes it back. And then the second pulse can't be sent out until the first echoes make it back. Now we're going to talk a lot over the next few chapters about how all of this works, and then we kind of put it together kind of in the mid part of the semester when we talk about transducers. But to understand this now is just going to help you kind of conceptualize everything that we're going to talk about, why things are related to each other the way they are. So let's go ahead and get into some of our parameters. So just like we did with the 7 parameters of sound, there are going to be certain characteristics that you're just going to want to know for these pulsed characteristics, or the 5 pulse parameters. So and they're the same ones as we did for just the regular sound ones. You'll want to know the units, if they have any alternative names, where they originate from. Is it the machine or is it the body? Can we change it, and then what typical values are. So I already kind of talked a little bit about this, but I'm just going to kind of recap just to keep going with the slides here. So pulse ultrasound is a group of cycles that travel together. So let's talk about that sentence real quick here. So up to this point, we've been seeing our ultrasound waves drawn out something like this, right? That is a continuous wave. There is no break within this wave. What we see with pulse waves then is something like this. There's a pulse, and then there's a break, and then another pulse is sent out. And that is really what is happening in ultrasound. So we talked about pulsed ultrasound being a group of cycles. So remember, this is a cycle, one peak, one trough. A group of cycles, so it can be 1, 2, 3, 4, sent together is a pulse. Now another concept that we need to know with the pulse wave is that we consider when this pulse is going out, this is on time. Right? And this break in between here, this is off time. And that makes sense Machine is on when it's sending the pulse. Machine is just listening. It's off when it's waiting for that pulse to come back. And so if you look at the continuous wave that I drew up on top there, you will see that there is no off time. And so that kind of makes sense too then, that the continuous wave, or CW is how it's abbreviated quite often, is always on. There is no off time. Okay. So again, pulse waves, or PW, have on and off time. Continuous wave only has on time. And here again is an example of our continuous wave versus our pulse wave. This transducer here, this is called a PDOF probe. It's used quite commonly in echo applications, and we'll learn why we like those continuous wave probes later in the or in a few chapters, not this chapter, in a few chapters. We'll learn a little bit more about that. And then here we have just kind of a regular imaging transducer creating those pulses. Ooh, one other thing that you guys have to know, write this down somewhere. Continuous wave imaging, or continuous wave probes, do not create pictures. All right? Pulse wave do create pictures. And so that kind of goes back to our transducer again. Remember, it would send the pulse out, and then it would go down and wait, and we'd have to wait for that pulse to come. Well, if there's always just a pulse going out and pulse going out, we're never going to get a picture back from that. We never really get the echoes back from that. So we cannot create pictures from continuous wave. So continuous wave, no pictures. Pulse wave, again, is what we use in our daily ultrasound for diagnostic medicine. We get pictures from pulse wave. Okay, so basics are out of the way. Let's actually get into the parameters here. So our first parameter is pulse duration. And pulse duration is often abbreviated down to just PD, if you see it in a formula. And this is the time it takes for one pulse to occur. So remember, our pulses are groups of cycles grouped together, and that's our pulse. And we want to know how long does it take for that to occur. Unit is usually in microseconds. Again, everything that we're doing in ultrasound is just so unbelievably fast that it's hard for us to even really conceptualize it, but it is in microseconds. Typical ultrasound value then will be 0.3 microseconds to 2 microseconds. And then this is determined by the source. So the machine is what determines the pulse duration, and I'll show you why in a second here. And then pulse duration is not adjustable by the sonographer. So again, pulse duration is going to ask how much time does it take for one pulse to occur? What is the time that goes by as this pulse goes by? And what is the time that goes by as this pulse goes by? So it depends on a few factors that we see in this pulse. So it has to do with frequency, it has to do with the number of cycles, and it has to do with the period. So let's take a look at these concepts then. So one of the things that I said is that pulse duration is determined by the source. And that is because a lot of the factors that go into pulse duration are also determined by the source. We said that frequency, when it increases, pulse duration is going to decrease. And so when we think about it, when we have high frequencies, we have short wavelengths, right? So we can fit a small pulse into a smaller time frame. This is going to go by much quicker than what a low frequency pulse would take. So remember, our low frequencies are going to be a little bit longer wavelengths. All right, so when frequency increases, we get shorter wavelengths, we get shorter periods. That all plays into how long our pulse duration is. Now the next thing that I said was that number of cycles also determines the pulse duration. So if we have a pulse here, a 3-cycle pulse compared to a 2-cycle pulse, which one's going to take longer? Well, that's going to be the 3-cycle pulse. So the more cycles we have within a pulse, the longer the pulse duration is. So cycles and pulse duration are directly related. And then the last thing that I have on that side is saying that when period increases, or when it takes longer for one cycle to be made, when we have lots of long cycles, that pulse is going to take more time than lots of short cycles. So period and pulse duration are also going to be directly related. The number of cycles that are in a pulse is determined by the machine, and it's really mostly determined by the maker of the machine. We know that shorter pulses create better images, and so most ultrasound equipment is going to have a short as cycle as possible to create the best pictures possible. All right, so just recapping this again, frequency and pulse duration are inversely related. As that frequency gets higher, our pulse duration is going to get shorter. Number of cycles and pulse duration are directly related. As there are more cycles in a pulse, the pulse duration will be longer. And then period and pulse duration are directly related. If the period is longer, the pulse duration will also be longer. Here then are a couple of formulas that have to do with pulse duration. And what I just want to point out to you is that these are how they are related in both period and then frequency. So this kind of tells us too that pulse duration and cycles and period are all related here. And we can tell when we have a formula situated like this, these are all directly related items. Or when you have a division in your formula, then you get indirectly related for that bottom denominator piece. So some other things to think about with pulse duration, and this is kind of stuff we've already just talked about. We have longer pulse durations, more time is spent creating the pulse when we have lots of cycles, long periods, and low frequencies. Where we have short pulse durations with fewer cycles, short periods, and high frequencies. And shorter durations are going to make better pictures. So our goal is always to have a short pulse duration. All right, our next parameter then is spatial pulse length, and we commonly see this abbreviated down to SPL. And this is if we could take a ruler out, measure that pulse in space, we would get a distance, and that would be our spatial pulse length. The spatial pulse length then is mostly measured in millimeters, typical value ranging from 0.1 to 1 millimeter, and this is determined by source and medium. Well, thinking back to chapter 3, do you remember what else was determined by source and medium? Well, that was the wavelength. And remember, the wavelength is the distance that one cycle takes up in space. So wavelength and spatial pulse length are kind of related in that way, in that they are determined, that spatial pulse length will be determined by the wavelength. And that is why then spatial pulse length is also determined by source and medium. This is not adjustable by the sonographer, just like wavelength is not adjustable. So now we're looking at a pulse in space. Again, if we could pull out a little ruler and put it up against this pulse as it sits in space, we could measure it then, and that would give us our spatial pulse length. So shorter pulses are going to have shorter spatial pulse lengths. And again, we have some relationships to talk about. So frequency and spatial pulse length are inversely related. As the frequency increases, the spatial pulse length will decrease. It'll become shorter. If the number of cycles increases, then the spatial pulse length will increase. And then if wavelength increases, the spatial pulse length will also increase. So let's draw a few of those ideas out again. All right, so our first one was that if frequency increases, then our spatial pulse length will decrease. So remember, when we have high frequencies, we have short wavelengths, right? So here is our high frequency pulse, and here's our low frequency pulse. If we were to pull a ruler out, oh, look at that, I have one right here. If we were to pull a ruler out and measure that, which one is going to be shorter? Well, we can visually see that the high frequency pulse is shorter. So when the frequency increases or gets higher, the spatial pulse length will be shorter. So they're inversely related. Number of cycles then determines the spatial pulse length as well. So here we have a cycle that is 3 cycles long versus 4 cycles long. Which one is going to have the shorter spatial pulse length? Well, again, we can visually see that it's the one with the fewer cycles. So if the number of cycles increases, then the spatial pulse length will also increase. That makes them directly related. And then lastly, if our wavelength increases, then our spatial pulse length also increases. And that kind of goes back to frequency, right? Because we know they're related. So let's say we have a pulse here with wavelength equals 1 millimeter. So this pulse, oops, sorry, I'm jiggling everything here. This pulse is then going to equal 3 millimeters. Where if we have a pulse that maybe has wavelength equaling 0.5 millimeter, then the SPL on this one would be 1.5 millimeters. And all I'm doing is taking that wavelength, counting how many cycles are in the pulse, and then multiplying it out. So we can see then if the wavelength is long, then the SPL will also be long. So they are directly related. And then here is our formula for spatial pulse length. And again, we can see kind of what we just talked about. When we have two items that are multiplied against one another to get our final answer, these are all going to be directly related. So the number of cycles increases, then SPL is going to increase. If wavelength increases, SPL is going to increase. And then just like we saw with pulse duration, there are a few considerations. We have lots of cycles, longer wavelength, and low frequencies. We're going to see longer SPLs. It's going to take more space, take up more space to create these pulses. And then when we have shorter SPLs, we have fewer cycles, shorter wavelength, and higher frequencies. And just like with a short pulse duration, a short spatial pulse length gives us better accuracy. All right, our third parameter of pulse waves then is the pulse repetition period. Pulse repetition period is often abbreviated down to PRP, and we define it as the time from the start of one pulse to the start of the next pulse. This is usually going to be measured then in milliseconds or microseconds. Typical value for ultrasound then is going to be 100 microseconds up to 1 millisecond, and this is determined by the source. So it is determined by the source initially, but the depth that you have your machine set to, that is going to be the biggest influence on PRP, or pulse repetition period. And because it is based on the depth, it is adjustable. If we adjust the depth that our machine is imaging to, then we are adjusting the pulse repetition period. So again, we are defining pulse repetition period as the time that it takes from the beginning of one pulse to the time of the next pulse. So that's going to include, pulse repetition period is going to include both the pulse duration and that listening time, that off time. How much time is in between there? So when you add the pulse duration and the off time, you get your PRP. As I've already mentioned, the depth of view is what mostly affects the pulse repetition period. And this is why it makes pulse repetition period adjustable. So when we say depth of view, we're talking about how deep do you have the machine set to image into the body. Usually on your ultrasound machine, along the side, you'll see a group of numbers with hash marks in between. This is our depth over here. And for this example, each dot here is 1 centimeter. So the depth of view on this machine is set to 16 centimeters. That's that last dot down here. So we are imaging from the transducer face 16 centimeters into the body. And if you recall, what I said at the top of the lecture is that that pulse has to come out, it goes down one scan line, travels all the way to 16 centimeters, and then the machine listens for all echoes that are coming from, at the most, 16 centimeters. So it's waiting for this very itty bitty tippy echo to make it all the way back to the machine, and then it'll send the next scan line down. Now the scan lines that go across most of our machines, hundreds of them, 200, 300 scan lines going across. So it is creating hundreds of scan lines to make one picture. And then the way we see it, it looks like a movie almost. So it's creating tons of frames per second, so it looks like a movie to us. So it's real life, so it's considered real-time scanning when it looks like a movie. So again, pulse repetition period is adjustable because you can adjust how deep you are imaging. So some relationships that we can talk about regarding pulse repetition period then is that if the depth increases, then our pulse repetition period is going to increase because there's more listening time. If the depth is decreased, then the PRP is also going to decrease because there's less listening time. So let's take a look at that drawn out. So remember that PRP is both the pulse duration. So there's our pulse duration. Here's the beginning of our next pulse. So it's both the on time plus all of the off time. So it is pulse duration plus off equals pulse repetition period. And we've been saying that going crazy with my markers. And we've been saying that we can increase this off time or decrease the off time depending on our depth. So I want to show you a couple examples of that. Let's see, I'm going to pull out some Play-Doh here. I think that'll help to describe this. So I'm just going to make a little Play-Doh ball. And we're going to say that my Play-Doh ball is the pulse. So if I have my hands, one hand represents the transducer, my other hand represents the maximum depth that that pulse has to go down to and then return back. Okay, so I'm going like this, back and forth, back and forth. This is pretty quick, right? Those pulses can bounce in between very quickly. There's not a lot of space in there. There's not a lot of off time. This hand is not waiting very long to receive the pulse back. What if I increase my depth? Now my hands are, they're right on the edge. My hands are further away. To get this pulse all the way down to this other hand and send it back takes a lot more time. So now I'm waiting, I'm increasing the amount of time that this hand is waiting for that ball to come back. So again, remember, close, Boop, 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 boop. Those go really quick. That's a decreased depth. That's very shallow imaging. Depth and transducer really far apart. That's going to be deep imaging. Okay. So let's draw it out another way then. Again, we have our pulse, our off time, and the beginning of our next pulse. Remember that next pulse can't send until the echoes come back from the first pulse. So let's say this first one is set to be 10 centimeters depth. If we reduce our depth to 5 centimeters, we are now going to reduce this off time. So here's our first pulse, and then here's our second pulse. We've reduced that off time because we reduced the amount or depth that we have to image to. So another example that I use too is to think about, you have a grocery list. Maybe you have to get 5 things on your grocery list. Let's say you have to get milk, bananas, cereal, coffee, and bread. Apparently we're having breakfast. Okay, so we have 5 things to get from the grocery store. And we have 2 grocery stores that are near our house. We have one that's 5 miles away, and we have one that's 10 miles away. So here's our 5-mile store, and here's our 10-mile store. Say it's the same speed roads to get there. They're both 30 miles per hour roads to get there. And the only problem is that these are bizarre grocery stores, and we can only pick up one thing at a time. So if I'm going to go get my milk, come home. My bananas, come home. My cereal, come home. Coffee, go home. And bread, go home. I can do that pretty quick. But let's say I decided to go to the 10-mile away store. Now I've got to go get milk, come home. Bananas, come home. Cereal, come home. Coffee, come home. Bread, come home. So there was a lot more time in between that 5-mile store and that 10-mile store. It's going to take way longer to shop your list. So again, PRP is the amount of time it takes for that pulse to go out, and then all those echoes to return from the max depth. So again, just to reiterate some of the things that we were talking about here with the pulse repetition period, it really plays into the fact that there is on time and off time. So remember that transmit time or on time is the same as pulse duration. It's when that pulse is active. And we cannot adjust this part. This part is set by the machine. It's the off time that we are able to adjust because we can adjust the depth. Less depth means less off time, means more pulses are going to be sent. More depth means more off time. It's going to be longer before that next pulse is sent. So again, just to show it again. Deep imaging, long off time. Shallow imaging, short off time. Now, one thing I really want to highlight about pulse repetition period, this has nothing to do with the period of the wave. Nothing to do with it. So if I tell you you've got a wave and the period of it is 1/10 of a second, so this is maybe what it looks like, and then you have another wave where the period is 1/20 of a second, so it's probably going to look something like that. It's going to be a little bit shorter. Nothing to do with what the PRP is, because PRP has everything to do with how long is it waiting in between before that next pulse comes. Okay? So do not confuse the two. They have nothing to do with one another. Period is a parameter of sound. It has to do with frequency. It's set by the machine. Pulse repetition period has to do with your depth. All right, pulse repetition frequency, our fourth parameter. We're almost done. Pulse repetition frequency then is abbreviated down to PRF, and it's known as the number of pulses per second. So that sounds familiar to frequency, and it's got the same concept going, but is not the same as just the frequency that of the wave. And we'll go over it. Just kind of how pulse repetition period had nothing to do with the period of the wave, pulse repetition frequency has nothing to do with the frequency of the wave. But back to pulse repetition frequency. So PRF is the number of pulses per second, and we also measure this in units of hertz. But look at the typical value, 1,000 to 10,000. Remember when we were talking about frequency for ultrasound, it's above 20,000 hertz? That's the frequency of the wave. Pulse repetition frequency tells us how many pulses are getting sent per second. So it is a much lower range. This is going to be determined by the source. And then this is also adjustable. If you can guess why, it's again because of the depth. So here we are again with some pictures. And all I'm doing here is I'm counting. We're going to say that these pulses are happening over the time of 1 second. So all I'm doing is counting how many pulse groups are there in 1 second. So 1, 2, 3, 4, 5. PRF is 5 hertz. This one has 3, so the PRF is 3 hertz. Remember that our US values are usually 1,000 to 10,000. So that'd be 1,000 pulses in 1 second, or 10,000 pulses in 1 second. So just like PRP, PRF is related to the depth, and that's because PRP and PRF are also related. They're reciprocals. So if the depth increases, the PRF is going to decrease. There's more listening time. Therefore, we're sending less pulses per second. If the depth decreases, or we are imaging shallow, then our PRF is going to increase. And that's because there will be less listening time, so we can send more pulses per second. So let's take a look at that again to drawn out. Adjust this here. Give myself a little more room. All right, so we were saying that PRF and depth are inversely related. When PRF increases, depth is going to decrease or be shallow. And when PRF decreases, depth will be increased or be deep imaging. And that is because, again, of that listening time. And it has, again, to do with the PRP. So let's draw another wave out here. Let's say we are imaging down to 10 centimeters again. We have 1 pulse, our wait time, another pulse, wait time, another pulse. Okay? So, and let's say this is all over again 1 second. Oh, you can't see that on there. 1 second. So what is our PRF? Again, we're just counting the number of pulses, this whole chain, number of pulses per 1 second. So we can look, we've got 3 hertz. So our PRF for this example is 3 hertz. And that's because we have these long waiting periods while those sounds travel all the way to 10 centimeters and come back. Let's say then that we have the sonographer adjust their depth, reduce it to 5 centimeters. Now we're measuring or imaging a little bit more shallow. So now the pulse can go out. It doesn't have to wait nearly as long to send another pulse. So again, this is all over 1 second. We can just count 1, 2, 3, 4. Now the PRF equals 4 hertz. So we reduced our depth which means we increased our PRF. And that totally matches up. We already wrote that down up there. Now we're just proving it. And the reason that the PRF was able to increase was because we took up less space with that off time, and we could fit more pulses into that 1 second. So let's go back to our grocery store example again here too. So now, again, we have to get milk, bread, coffee, cereal, and I can't remember what the other one was. We'll say donuts this time. Donuts are delicious. And again, we have our grocery store that's 5 miles away, and we have our grocery store that's 10 miles away. This time, though, we've got company coming over for breakfast in 20 minutes. And I still have the same problem. These grocery stores are so weird. I can only go and get one item and I have to come home. Which grocery store is going to help me get more of the items on my list in those 20 minutes? Is it the 5 mile or the 10 mile? Well, just thinking it through, clearly being closer to home, I can get more from my 5 mile away store versus my 10 mile. So again, we go out, we get our milk, return home. Get our bread, go home. Cereal, coffee, donuts. Compared to milk, bread, cereal, coffee, donuts. Maybe I could get 3 of these items in my 20 minutes. And maybe going to the 10 mile store, I could only get 1 of my items in 20 minutes. So this is just kind of another roundabout way of showing us that when we image shallow or when we stay close to home, we can get more pulses or more of our grocery items from our list within the time frame. Now, our example was 20 minutes, but remember our time frame for ultrasound is 1 second. How many pulses can we send out in 1 second? So that is why it all is related to depth. And I had mentioned this earlier, and I kind of already showed you the slide. Let's go back to it here. That PRP and PRF are related. And if you look at our formulas, you'll see that they are reciprocal. So they have that special relationship that PRF multiplied by PRP is going to equal 1. So just like period and frequency, this is the only way that they're related to one another. Just like period and frequency, they are reciprocals to one another. So if you know one, you just got to plug it in and you can get the answer for the other one. So going back to our examples here, remember we had some examples where we could only fit in 3 pulses in our 1 second. So that PRF then would equal 3 hertz. That means then that our PRP is 1 over 3 or 0.33 seconds. And so what that is telling us then that it takes 1/3 of a second for this to occur, and then this to occur, and then this to occur. 1/3 of a second for each of those, both the on and off time. And as I've mentioned a few times already, pulse repetition frequency has nothing to do with the frequency of the wave. Again, we could have a wave that is, say we have a wave that is 10 megahertz, and we have a wave that is 2 megahertz. They're both going to go into the body. They're both going to travel the same speed. It has everything to do with how far they have to travel. How far is that store away? Is it 5 miles or 10 miles? All right, last parameter, duty factor. Duty factor is quite often abbreviated down to DF, and it is the percentage of time that the system is on. There is not a unit. This is one of our first unit list numbers, but it is a percentage, so you always want to make sure that you're writing it with the percent or leave it in decimal form. Now, a typical value of the duty factor is going to be somewhere between 0.2% and 0.5%. Remember, that's for our pulsed wave imaging probes, where duty factor of the continuous wave again does not produce images, that's going to be 100%. And that's going to be 100% because if you think about it, it's 100% of the time always on. It's just on. There's no listening time. So that's a good test question right there. What is the duty factor of continuous wave? 100%. This is going to be determined by the source. And again, this is determined by the source because it goes back to being determined by the pulse duration and the PRP. And duty factor can technically be adjusted by the sonographer because it is adjusted for depth. So here is yet another one that is adjustable by that depth. So we're going to take a look at that. So duty factor is asking and answering the question, what percentage of time is the machine on? So we know that we have our pulse duration and we can calculate how long that pulse is taking. We then look at our PRP, which includes both the pulse duration and the off time. And we divide the on time by the entire time that pulse and off time took. So in our example here, we have half a microsecond divided by the 100.5, or the half microsecond for pulse duration, and the 100 off time. So we take that 0.5 divided by 100.5, and in the end our duty factor then is 0.498%. So about 0.5%. And duty factor formula then, it is related to both the pulse duration and the PRP. So pulse duration divided by the PRP, you can leave it as that number there. If you want to change it into a percentage, then you multiply it by the 100 to get your percentage. Just some more comments on what duty factor means for the machine. So duty factor has to be more than 0. If the machine is off, power off, duty factor is 0% at that point. But if the machine is on, it is sending pulses out. And so there must be some range between 0 and 100%. So more than 0%, it can't be 0. Less than 100%, can't be 100%, unless we have a continuous wave. The only way it can be 100% is if we have a continuous wave probe. Clinically though, remember, duty factor is only like 0.2% to 0.5%. So what this means in the end is that the machine is listening way more than it is spending time sending pulses out. So I already mentioned that duty factor is related to depth. And in general, if the depth increases, then the duty factor is going to decrease. That's because there's more listening time, therefore less pulses per second, therefore there's less on time. If the depth decreases, or we move more shallow, then our duty factor is going to increase. That's because there's less listening time. That means there's more pulses per second, meaning there's more on time. So let's take a look at this concept. All right, so again, we have our pulse going out, we have our listening time, and our pulse going out. And I'm just going to use some whole numbers here just to kind of show you the concept. So let's say we are, again, imaging at 10 centimeters, and our pulse duration, again, just using numbers, is 5 seconds to put the pulse out and 20 seconds to listen. So we are then going to take our pulse duration, get rid of this for a second, our pulse duration divided by PRP. And if you remember, PRP is pulse duration plus the off time. So we have 5 divided by 25, and that gives us 0.2. And then we need to multiply that by 100. So you can leave it as 0.2. I would prefer, though, just to kind of get used to it, that you do offer this as a percentage. So 0.2 times 100, we get 20%. All right. So that is saying that this 5-second pulse is on 20% of the time when we are set to this depth. So 20% of the time it is pulsing, 80% of the time it is listening. That's what we're seeing with this 10 centimeters. All right, let's take a look then. What happens if we change this to 5 centimeters? We reduce the depth that we're imaging to. It's a little bit more shallow. All right, so remember we had 5 seconds to send out the pulse. Our off time is quite a bit shorter now because we're imaging more shallow. So our PRP is going to decrease. So it was 20 seconds. Let's say it's now 10 seconds. So again, we're going to take our pulse duration and we're going to divide it by the PRP. Remember, PRP is the pulse duration plus the off time. So now we have 5 divided by 15. So 5 seconds divided by 15 seconds gives us 0.333. We'll multiply that by 100 and we get, we'll just say 33%. So now we decreased our depth, which means we've increased our duty factor. The duty factor is on more. Now the machine is sending pulses 33% of the time and only listening 67% of the time. Okay. So before, with our 10 centimeters, it was pulsing 20% of the time and off 80% of the time we're listening. So that shows us, again, proving that when we decrease our depth, our image shallow, our PRP decreases because our off time decreases, and because of that, our PRF is going to increase. And if our PRF increases, we have more pulses, we're pulsing more percentage of the time, so it makes sense then that our duty factor will also increase. All right, so that's a lot of concepts kind of layered on top of one another. But remember, duty factor, PRF, PRP, that should be in our, all have to do with your depth. Okay? Any luck, the next slide, yes, is our summary then of all of that. So when we have shallow imaging, we're 5 centimeters, 2 centimeters, we're shallow imaging, there's going to be less listening time, which means there's a shorter PRP, a higher PRF, and a higher duty factor. When we're imaging deep, we're listening more, we have a longer PRP, lower PRF, and lower duty factor. The last slide here then is just kind of a nice overview of everything that we've talked about, and if it's adjustable, what the units are, just a nice way to kind of map it all out. So let me know if you have any questions about these parameters. You will again get an opportunity to do some math. Remember, your workbooks are much more math heavy than your tests will be. But what I want to know is, do you understand how these parameters are related? And by knowing the formulas, you can kind of plug information in to your parameters. Let's take a look just as an example. Say you do remember that pulse duration over PRP is our duty factor. Say you remember that formula kind of loosely, and then I say, well, the PRF is decreased. What happens to the duty factor? Well, maybe you can't remember off the top of your head how they're related, but you do remember the formula. So we can plug numbers in. So let's say, just doing some quick math, let's say we did 5 divided by 10 at first. Our duty factor would be 2. Well, then let's say we reduce the PRP part of it, so 5 divided by 5. Well, now it's 1. Well, that tells us then that if PRF goes down, now we can kind of plug some fake numbers in and figure out that duty factor goes down as well. So again, by no means are you going to be able to use a calculator on your boards. It's going to be a lot more concepts like this. Do you know how to apply the formula? Can you tell me how these items are related? The more you understand about these relationships, the easier it's going to come. The more you're going to be able to understand what's happening with the machine and the physics behind it. Most people are going to try to memorize. If memorization works for you, 100% fine. But I can guarantee you this is going to stick longer. You're going to do better on your boards. You're going to do better on your tests if you can understand it. So try the math, write down your formulas, have them handy, study your formulas, so you can then understand what the relationships are between these parameters. All right, we'll see you in a bit for the next section, Chapter 5.